Okay, so thank you, Romain, and the organizing team for PAW today. So good morning, everyone. My name is Loïc Alexandre. I'm a PhD student at the Laboratory of Fluid Mechanics and Acoustics in Lyon. And today I will be presenting the study we've carried out with my supervisors, Pierre Lecomte and Marie-Annick Galland, with the help of Maxime Popov, present here today from the City Lab, from here. So the study focuses on feedback active noise control using Faust on a FPGA platform with an application to noise reduction in headphones. So before I start explaining the principle of feedback active noise control and show you how we used it, I want to give you a little bit of context for you to understand. So this study and actually my PhD are part of the FAST project, which is a national research project gathering the GRAM, the City Lab, and the LMFA, my laboratory. And in the context of this project, the City Lab and the GRAM developed a toolchain called the CFALA toolchain, and it allows us to compile a Faust code in order to use it on the FPGA platform. So the idea is to use this CFALA toolchain for a practical application and actually with some educational interest. Just for you to know, Maxime will be presenting their work later this morning, so you will be able to see his presentation. So, as I was saying, there were some educational interests because actually the laboratory, the LMFA, is on the campus of École Centrale de Lyon. And the school uses the installations from the lab for some practical works. And one of them focuses on feedback active noise control in headphones. The thing is that currently, at least until the past year, they were using a quite old analog filter with fixed parameters, so it was not really flexible for the students to change them and see what's happening, the result in real time. So the idea is to use Faust, the CFALA toolchain, and the FPGA to kind of upgrade this experimental bench. Okay, so now that you have the context, I'm going to explain a little bit the principle of feedback active noise control and show you how we used it with Faust. Of course, nowadays the headphones with active noise cancelling, it's pretty known and easy to find. Usually the idea is to cancel, to attenuate a disturbing noise, for example here the noise from the aircraft. But when a company develops a headphone, usually they are able to optimize everything in this particular headphone. In our case, the idea is more to transform a passive headphone into an active one with the idea that it has to be academic so the student can understand the principle. So since we cannot use the students as guinea pigs, we use the dummy head, the one you saw just on the picture before. And it has two microphones located simulating the eardrums of the listener. And for the control microphone, which in the case of a company headphone, it is located at the optimal position. In our case, it is an external microphone placed inside the ear, just to be able to change the headphone, replace the passive headphone. Okay. So taking this setup into account, we can imagine this scheme with the idea of reducing the pressure from a primary source at the eardrum microphone. So to do so, we need to introduce a secondary source, which in this case is the loudspeaker from the headphone, and the control microphone placed close enough to the eardrum microphone so that if the pressure is reduced at the control microphone, we assume it is also at the eardrum microphone. The question now is, what is the signal feeding the secondary source, the loudspeaker from the headphone? Well, to process this signal, we need to introduce the feedback loop composed of an amplifier with pure gain, not depending on the frequency, the control filter, and we'll see in a little bit what it looks like, and finally the transfer function between the headphone loudspeaker and the control microphone, which is called B here. Okay, taking this into account, we find that the total pressure at the control microphone is now equal to the pressure from the primary noise, plus the total pressure itself going through the feedback loop. With this expression, we get this ratio that we actually want to minimize in order to reduce the pressure. And to do so, the only thing we can act on is the frequency response 8 dB. And the thing is that there is an unstable case when 8 dB is equal to 1 because of the division by 0. So in summary, what we want to do is to increase the modulus of 8 dB, but not for the frequencies where the phase is equal to 0, because then we can have the unstable case. Okay, maybe to make it more clear, we can see a practical case. So this is a measurement made from the experimental bench. And you see that in this case, it's just dB, so there is no control filter. And the amplitude is in decibels here, so the instability will occur when the amplitude is equal to 0, not 1. You see on the phase response that the frequency, well, the phase crosses 0 at the frequency 5,169 Hertz. The thing is that at this frequency, the amplitude is almost the maximum amplitude of the frequency response, which means that normally when we increase the gain to actually apply some noise reduction, in this case, no attenuation will happen before the instability occurs. And in practice, the instability, it is the audio feedback, a really high annoying pitch. So in this case, we actually cannot have noise reduction. So this is why we need to introduce the control filter. But before designing the filter, we need to answer the question, what actually do we want to do physically? Well, since the headphone itself, the material will help attenuate the sound in the middle and high frequency, we want to focus the active noise control in the low frequency band. So here we actually focus between 50 and 1 kilohertz. So the filter should amplify the amplitude in the low frequency, but without changing too much the phase response, because we don't want the unstable frequency to shift inside the frequency region of interest. So one option to do that is a backward filter designed using 2 complex conjugate poles and 2 complex conjugate zeros. And you see on the right hand side that we focus on 2 parameters, the frequencies and the damping factors of the poles and zeros. So on the left hand side, you see that the filter is actually doing what we want, amplifying the low frequency band, but the phase response is equal to 0 outside of the frequency range of interest, 50 Hertz, 1 kilohertz. Okay, so this is great. If we introduce this control filter inside the feedback loop, we obtain now this result. You see that the unstable frequency is more or less the same as before, 2 Hertz higher actually. But now the amplitude at this unstable frequency is not the maximum anymore. We have an increase, a peak in the low frequency, which actually comes from the control filter we just introduced. So this gain margin we have is actually the attenuation we'll get when increasing the gain. The low frequency will be amplified, but before we get instability, we will have attenuation happening. Okay, so this is great. It is what we can do currently in the experimental and the practical work. But the thing is that the student cannot change the parameters in real time and see what is the results, is it better or not for the noise reduction. So this is why we introduced the incredible Faust and the FPGA. Basically what we did is write a simple script. We define the frequencies and poles of the filter. Then we get the coefficients, the analog coefficients from it. And the TF2S function is doing the bilinear transform in order to get the digital filter. Of course, with digital filtering comes the latency. With the FPGA, we are using a sample rate of 192 kilohertz. We get a latency of 80 microseconds. And you might have noticed that the frequencies and damping factors are defined using sliders. This is just to get the graphical user interface for the students to actually change the parameters. Okay, so if we take the same example as before, a single backward filter, really similar to the analog one, but this one is digital. Still doing the amplification in the low frequency, but you see on the phase response that now we have a slope, and this slope corresponds to the 80 microseconds of latency. So now if we introduce this first digital filter inside the feedback loop, we see that the unstable frequency is shifted to 3000 Hertz, more or less, which is lower than the previous one. But in this case, there is a particular and interesting phenomenon, is that for this frequency response, which corresponds to one position of the headphone and one position of the microphone, the control microphone, well, in this case, shifting the frequency, for this new unstable frequency, the amplitude is actually lower, which means that now we have a bigger gain margin. So normally we'll be able to even increase even more the gain and obtain a better noise reduction. So we will see in a little bit if it is true. But what is really great with Faust and the FPGA is that it is really easy to change the configuration of filter. In this case, we can set two backward filters in series. The idea of this is just to broaden a little bit the frequency range of attenuation. And you see on the amplitude that it is still doing the same, amplifying the low frequency, but here in a larger frequency band. And of course, on the phase response, we still have the slope because of the latency, which is the same in this case. Now, if we introduce this new digital filter inside the loop, we see that the frequency of unstable frequency is again shifted a little bit, but still the amplitude is even lower than the previous case. And we still have this peak in the low frequency, which will help doing the noise reduction. Okay, so now that I showed you some cases, we can see actually what are the results and do we obtain a noise reduction. This is the noise reduction for the two single backward filters. What we do basically in the measurements, we take the case without feedback loops, so without active noise control. We do the measurements at the eardrum microphone, and then we do the exact same measurement using as a primary noise an external loudspeaker. So we do the exact same measurement, but using the feedback loop and the active noise control. And what you see on the left-hand side is just the ratio of both measurements. So you see that for both cases, we have noise reduction on a quite reduced frequency band, but it is a bit higher for the digital filter, and it is what I said before, the gain margin is better, so we actually get a higher noise reduction. But what is more interested in our case is when we want to broaden a little bit the frequency range of attenuation. With the series of two backward filter, we get higher noise reduction and broaden frequency range. Okay, so just to conclude, using Faust, the CFALA toolchain, and the FPGA, we are able to get noise reduction to actually match what we would have with analog filter and even have a better result up to 20 decibels. But the real interesting thing with the Faust and the FPGA is the fact that we're able to change the parameters, to change the design of the filters in real time and really easily using Faust. Of course, with the digital filtering, the drawback is the latency, but we've seen that depending on the case, on actually the position of the headphones and the control microphone, it can be limiting the frequency range of noise reduction. Talking about the position of the headphones and the case, we could actually think about an automatic adjustment of the filter, the parameters, in order to get a noise reduction and avoid the unstable frequency for any case. We could also use the latency. You saw that adding latency was actually better for the noise reduction. We could imagine adding some delay to actually get a better result. And I guess we cannot chain an infinity of biquad filters, but actually a student already started to work on it during an internship. And you see on this picture that the FPGA is not anymore like a mess on the table. So this is a 3D model made by Maxime Popov, present here today. So yes, there are still a lot of work, lot of future work we can imagine, but since in our case we're not looking for a company and making a active noise cancelling headphone, this is just for academic purposes. Thank you for your attention, and if you have questions, I'm happy to answer them.
Questions?
Yeah.
You said the latency is about 50 microseconds?
80, yes.
18?
80.
Wow. 80? Okay.
Yeah.
Do you think it would be better if it would be lower? Do you think you could get better results with lower latency depending on the situation in general?
Yes.
Or is it just you were lucky in that case and it actually helped you?
Yes, I was lucky in that case because it was not limiting too much the frequency range of frequency. It was actually helping having a broadened frequency range. But yeah, in general, it is better having the lowest latency possible. This is why normally we use analog filter, because then we could imagine, okay, if we actually want to shift the unstable frequency, we could do it with an extra delay. It is better to be able to do everything and add some extra delay than having to be limited by the latency at the principle. Mm-hmm.
Yeah. But, thank you. Other questions?
I just want to say, for those of you who are watching us online, you can also ask questions through the chat, and we can ask them to the presenter. So if you have questions, feel free to ask them directly in the chat. So yeah. Other questions in the room? Yeah.
I was just wondering about how this would work if it went into commercial production with the FPGA. Would you anticipate embedding this on an FPGA in headphones, or would you put it on an ASIC or something?
Yeah. I guess some headphones already use FPGA in their company headphones. But yes, of course you have to reduce the size of the FPGA and add a lot of security filters, because it's really easy actually to get this unstable frequency. So you wouldn't want this to happen for like customers. So you have to add some security filters, and also right now it is just the noise, the external noise is just a noise, and we reduce this noise. But in the real case, there is also some music playing. So I'm sure in this case the spectrum of the music would change a little bit, adding this active noise control. And maybe you've heard this when you put some active noise cancelling headphones. Sometimes you kind of hear another noise in the background. It comes from this feedback loop. But yes, in this case, we will have to add some other filters to be sure it works for music and in a real case scenario. Mm-hmm.
Thanks.
Still no questions on the chat? Okay, well, thank you, Loïc.
You're welcome.
So our next presenter is going to be Fernando Lopez Lescano, who's visiting us from Stanford University in the United States, and he's wearing Ping, the penguin. Okay, so we're going to have to stick to the schedule, so we're going to have to wait until 10 for those of us who are watching the conference remotely, you know, like, so that it makes sense, you know, like, so we'll probably have like 10 or 5 minutes, so if you want to go get a coffee, if you didn't have time to get one or whatever, like, feel free to do it, but the next presentation, next talk is going to be at 10, so thank you.